Previously, we have shown that the OLS estimators can be evaluated using these formulas. As we know that these parameters are estimated using a data sample obtained from the population sample. And since the sampling procedure is random, different data samples could render different values for the estimators. To help gauge how good our estimators are in predicting the population parameters, we need to learn about the variability of our estimators. Specifically, we want to know how do these estimates relate to the true population values, and how variable are these parameters from one sample to another. These equations here tell us that the estimated beta 1 hat is given by the true beta 1 plus a second term. The second term here is dependent on the level of covariance between x and u and the variance of x. What this means is that if the least squares assumptions hold, then the second term is 0 and hence should go away. Then the expected value for beta 1 should be equal to the true beta 1. In other words, the OLS estimators are unbiased if the least squares assumptions hold. Additionally, if the least squares assumptions hold, then based on the central limit theorem, the distribution of the OLS estimators is approximately normal if the sample size is large. Formally, if the least squares assumptions hold, then the beta 1 hat follows the normal distribution with a constant mean of beta 1, and which is the true population parameter, and the constant variance. The variance of beta 1 hat is given by this formula here. The standard deviation of beta 1 hat is also known as the standard error of the slope, is the square root of the variance. The standard error of the slope is a very important measure to help gauge how good our estimated beta 1 hat is in predicting the true beta 1. Ideally, the standard error of the slope is the smaller, the better. The standard error will also be a critical component in the hypothesis tests that tell us whether a given variable should be included in the regression model. And therefore, it is very important that we understand the properties of the standard error before we move on to the next topic. Let's look at some simulation results here to learn about the properties of the standard error. I designed this simulation so I know exactly how the true relationship between x and y is defined. I also defined the sample size and the distributions of u and x. In this example, y is given by x plus u. The sample size is 100, and u follows the normal distribution with a constant mean of 0 and a variance of 0.09. And x follows the standard normal distribution. As you can see in this plot, the distribution of the scatter plot is relatively linear. So a linear fit appears to describe the underlying data pretty well. The estimated slope is 1.03, which is very close to the true slope of 1. And the standard error of the slope is 0.03, which is very small, corroborating with what we have observed in the plot that the line is a tight fit for the data. In this simulation here, I defined the new relationship for x and y. Specifically, y is given by the exponential of x plus u. The same sample size and the same distribution for u and x as in the previous example. But in this case, the distribution of the underlying data is not linear at all. And by fitting a linear line on the data, we failed to describe the relationship for the underlying data. Hence, you see that the estimated slope is very off. It's a 1.76 versus 1. and the standard error of the slope becomes much bigger than before. It's 0.13 versus 0.03. By comparing the results of the two simulations, we can conclude that the standard error of the slope tend to be smaller if the regression fits the underlying data better. In this simulation, the relationship between x and y is still exponential, but I increased the sample size from 100 to 1000, everything else equal. By drastically increasing the sample size, the standard error of the slope becomes much smaller. It's now 0.04 versus 1.13. In sum, we have learned that the standard error of the slope tends to be smaller if the regression fits better or if the sample size becomes larger. This simulation posits that y is given by 2x plus a random error term. Sample size still 100, and the distributions of u and x are the same as before. Since the underlying data is linear, and therefore a linear fit on the data describes the relationship really well. Hence, we see that the estimated slope of 1.97 is very close to the true slope, which is 2. And the standard error is also very small, it's only 0.02. In this simulation, the relationship is the same. The only difference is that the distribution of x now has a much wider variance. The variance is now 4 versus 1 from before. Everything else equal, increasing the variance of x causes the standard error of the slope to decrease. It used to be 0.02, but now it's 0.01. Therefore, we want our independent variable to have a wider variance, because the wider the variance of x, the smaller is the standard error of the slope. In summary, we have learned that the following factors tend to drive the standard error of the slope estimates. If the regression fits better, and if the sample size is larger, and if the variance of y is greater, then our standard error of the slope is smaller. Now let's move on to look at a California schools example again. In your quiz, I want you to add the CSE function to your R script before you run the regression output. You will just copy over this chunk of code and paste it into your script and run it before you run your OLS estimates. You can use the Stargazer function to neatly format your regression output into this table here. The regression output shows you what is the estimated beta 1 hat and what is the estimated beta naught, and their respective standard error of the estimates. The standard error of the estimates are always included in the parentheses. For example, the standard error for the beta 1 hat is 0.519, and the standard error of beta naught is 10.364. You can also see what is the sample size and the goodness fit measures for this regression. The sample size is 420, and R-square is about 5.1%, and SER, or the residual standard error in this case, is 18.58. In the wedge example, similarly, you see what is the estimated slope, what is the estimated intercept, and their respective standard errors reported in the parentheses, the sample size, and the two goodness of fit measures. Now let's pause this video to do the in-class exercise 7.